All right. If you've been looking at the checklist, you will see we're getting close to the end, as we should be, since it's close to the end of the semester. The last three topics are all about the same general thing, and that is a thing called the traveling salesman problem. The traveling salesman problem, which I will usually abbreviate as TSP. This is a very famous sort of graph theory type problem that's very important in the real world today. It's not exactly like an unsolved problem, but it's a particular type of calculation that people need to do all the time, and it's called the traveling salesman problem. And it comes up in various different settings, and we'll talk about that. But this is about Hamilton circuits, although it's not about finding Hamilton circuits. So this stuff that we've been doing the past couple of times, this is really completely different, although it's still about the concept of Hamilton circuits. Anyway, this is about, it's all about Hamilton circuits in certain types of graphs, which are called complete graphs. Some graphs are called complete. Actually, most of the graphs that we have ever talked about are not complete. If you just sort of make up a graph at random, it's probably not a complete graph. A complete graph, here's the definition. Complete graph is one where all pairs of vertices are connected by edges. It means every vertex has an edge to every other vertex. That's called complete. And it's called complete because that's like it has all the possible edges that could possibly exist in a graph. So that's why it's called a complete graph. So for example, here's one. 3 vertices, every vertex is connected to every other vertex. That is a complete graph because all of the pairs of vertices are connected by edges in this case. There are no 2 vertices that don't have an edge, all right? That is a complete graph. And actually the complete graphs have names. This one is called K3. K for complete, I guess. I'm not sure actually. I think K, there was a famous graph theorist, Polish graph theorist named Kuratowski, who I think the K is in honor of his name. But anyway, this is the complete graph on 3 vertices. This is how I might describe that. The complete graph on 3 vertices. This is the only complete graph that you can make with 3 vertices. It's just 3 vertices and everything is connected to everything else. All right, the complete graph on 4 vertices, which is called K4, looks like 4 vertices and they are connected. Everything is connected with everything else, which looks like that. So I have the lines crossing there, but there's no vertex in the middle. This is just 4 vertices and every vertex is connected to every other vertex. That's the complete graph on 4 vertices. What's the complete graph on 5 look like? You could start with sort of a 5 vertices arranged in a pentagon, if you will. This is going to be a picture of K5. And then every one of these is connected to every other one by edges. Like that. This is K5, etc. All right? These are all complete graphs. I'm sure if you wanted to, you could draw the complete graph on 6 vertices. Start with 6 vertices, kind of in a hexagon, and then just put every possible edge in there with every other possible edge. All right, these are called complete graphs. And what we want to talk about, like I said before, the traveling salesman problem is all about Hamilton circuits in complete graphs. So, for example, maybe I'll just draw this K5 again, and I'm just going to name them A, B, C, D, E going around, and then I'll put all the edges like that, right? These are all the edges. Every vertex is connected to every other vertex. Here I'm drawing the vertices just with the letters, all right? Can you find a Hamilton circuit in this graph? So a Hamilton circuit in this graph would be like, remember what a Hamilton circuit is? It's a circuit, so it starts and ends at the same point, but it goes around the graph and touches every vertex once. So for example, I'm going to draw a Hamilton circuit. It could do something like that one. That is a Hamilton circuit because it touches every vertex once and comes back where it starts. Now you might be concerned that doesn't that have a sub-circuit, which is not allowed? That does not count as a sub-circuit because, well, let me just say, can I write down those numbers or those letters? I just said A, D, C, B, E, A, right? It looks like that, right? You should be at least slightly worried that this is not a legal Hamilton circuit because of a sub-circuit. It looks like there's a sort of a sub-circuit right there. But this actually doesn't count as a sub-circuit in this case because that's not a vertex, right? So this is not making an actual sort of closed circuit in the graph. This is just a place where the lines happen to cross, but that doesn't represent an actual intersection or an actual vertex in the graph. So this is a legal Hamilton circuit. It covers every vertex and comes back to the beginning. A, D, C, B, E, A, right? Can anybody see another? There are actually many more Hamilton circuits in here. Can anybody tell me? Maybe just shout out. Or how about also starting at A, but is there another Hamilton circuit somebody can see? There's some fairly obvious ones, I think. Anyone feeling obvious this morning? You just have to visit every vertex and go back to the beginning, to wherever you started. Anybody see another way to do it? Yeah?
A, B, C, D, E, A.
Yes, this is what I was referring to when I said there are some fairly obvious ones. You could just go around the outer perimeter, right? That certainly makes a Hamilton circuit which visits every vertex and comes back to where you started, all right? Or how about this? A, D, B, E, C, A. Is that one? I actually just made that up. I wasn't even looking at the picture, but maybe you can do this with your finger. Does that actually work? A to D to B to E to C to A. That actually makes this sort of star shape, right? That one looks like ball, 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 ball. Anyway, it does hit all the vertices without repeating any, so it is a Hamilton circuit. All right, that's what this one would look like. I just made that up without even looking. Actually, it is. It's not so hard to believe me if I tell you. You could just list out these vertices in any order you like, and it will automatically be a Hamilton circuit. You might be concerned about, like, is there actually going to be an edge between B and E? But the answer is yes, because this is a complete graph. It means every edge you would want to be in there is already in there. And so actually, any rearrangement of the vertices, of course you can't list the same vertex twice, but you can just write A, B, C, D, E in any order you want, and it will make a legal Hamilton circuit. Any rearrangement of the vertices makes a valid Hamilton circuit. All right. Would you mind, every so often I may use the word permutation. This is the fancy mathematical word for rearrangements of letters or whatever, right? We also use that word when we were talking about the Shapley-Shubik, the perms. Those are just different ways of rearranging the letters. And it is also relevant for the sake of these Hamilton circuits, all right? So any rearrangement of the vertices makes a valid Hamilton circuit. And there are actually many, it would be a lot to write down all of the possibilities. So in this case, in this graph, complete graph K5, if we start and end at A, it'll look like one of these rearrangements will look like A, something, 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 A, right? Where these things in here, this can be any rearrangement or any rearrangement of B, C, D, E. So you could put them in exactly that order, B, C, D, E, and that would be one Hamilton circuit, but any other rearrangement would also qualify. And there's a lot of different ways to write B, C, D, E in different orderings, all right? In this case, actually, any rearrangement, there are 24 in this case, 24 different possible ways to rearrange those letters. How you get that? It's actually 4 factorial, if you're familiar with the factorial operation. Doesn't really matter, though. All right. These are Hamilton circuits. So, generally speaking, in a complete graph, there are many Hamilton circuits. And if it's a really big graph, there's kind of like too many to even write them all down. Like for 5 vertices, there's 24, which that's certainly more than I would want to write down, although if I really had to, I could write down all 24. It's not such a big deal. But in a bigger one, there are way too many. So in a complete graph, there are many, many Hamilton circuits. For really small ones, it's not so bad, but for big complete graph, there's really many, many Hamilton circuits. All right. What does this all have to do with? I said, this is actually an important problem in the real world. It's actually something that people have to deal with every day. Not really me personally, and probably, I don't know about you, your personal lives. You may have encountered some traveling salesman type situations in your own life. I'm going to try to give you, this is a little real world example here. These kinds of Hamilton circuits in complete graphs. Complete graphs. IRL. This is inspired by true story, but this is somewhat made up. I don't really think about this in my own personal life all that often. But here is my holiday travel plans. This is a true story about my own married life. #married life. Around the holidays, all the grandparents want to get in on the holiday festivities, and so you have my parents. By grandparents, I mean my parents. They are the grandparents of my kids. My parents and my wife's parents, and they both want us to come to their house for Christmas, which is typically not possible. But anyway, here's my situation here. I'm going to draw a sort of a little map here. Here's me in Connecticut. This is where I live. My mom and dad live near Boston, so over here. My mom and dad in the great state of Massachusetts. All right. My wife's parents, who I refer to as Gigi and Pops, because that's their grandparent names. Those are my wife's parents. They live in New Jersey. And we live right about equally distant between the two of them. One of the reasons why I was interested in working at our dear university is because it is ideally situated between the two grandparents. One of them would feel bad if we lived closer to the other one. And then we also, around the holiday time, we also want to visit Aunt Megan, which is my wife's sister who lives in Pennsylvania. I'll put that over here. So here's Megan in Pennsylvania to see my kids' cousins. All right. So every Christmas or whatever, we have to go to all of these places, of course, starting and ending at our own home. So we must travel to each of the 3 places. And of course, we want to start and end at the star, which is our home. All right. Now, these places, we can consider them to make a graph just in terms of what are all the various ways that we could go somewhere from somewhere. So we could go from my house to my parents' house, and then from my parents' house to Megan's house, and from Megan's house to Gigi and Pop's, and then back to my house. Like, that would be one way to do it. But of course, there are many other ways you could have done this. We could have, say, gone to Megan's house first. We could go like that, and then down to here, and then back up there. So there's actually other edges, kind of those two diagonal type edges, meaning it is possible to drive from here straight to Megan's house, and then maybe go down here, and then go all the way up there, and then come back, and so on, right? These are all the possible individual routes. And when I say we must travel to each of the three places, starting and ending at the star, this is the same as saying I want a Hamilton circuit, because a Hamilton circuit is a circuit starting here, which visits every vertex once and then comes back where we started, all right? Certainly we don't want to revisit a vertex here because that's just like extra stuff. So we must travel to each of the three places, starting and ending at the star. What all of this means we want a Hamilton circuit. That is something which visits each of those three different vertices and then comes back to the beginning. And when you do this in real life, you don't just want any Hamilton circuit, you want one which is kind of like the best one or the most convenient one. In this case, you would like to choose one which has the least amount of total driving time or the least amount of distance or something like that, all right? So we want a Hamilton circuit, and I will say, in general, the traveling salesman problem, which is what we're talking about here, is about finding the optimal, that is to say the best, which usually in a problem like this means shortest, Hamilton circuit in a complete graph. All right, in this case, we would like to visit all three of those places in the shortest total distance. So we don't want to be driving back and forth along the same place or driving an unnecessarily long distance. All right, finding the optimal shortest Hamilton circuit in a complete graph. Now, in my own personal life, it's not such a big deal if I really drive precisely the best possible route, because I mean it really doesn't matter that much to me. Although there are serious businesses in real life where they really want to drive the best possible routes, and in much more complicated situations. So I will just say this comes up in many, many places in real life. For example, for let's say the underpaid Amazon delivery guy. The Amazon delivery trucks, right? The idea here is the Amazon truck starts its day with, I don't know, like 200 packages in the back and a list of 200 addresses where these packages have to go. How do you decide which ones I should do first? Like, in what order should I drive the route? This is the same question, really, as what I was asking up here. I mean, this is a very simple version where there's only 3 destinations, and I want to know what's the best way to drive across all 3 destinations. But in this case, the delivery truck has something like 200 destinations, and it's not at all obvious how to decide which order you're going to do them in, right? I mean, if all the houses live on the same street, you can just do one by one, but they don't all live on the same street. They live all over the place, right? So this comes up for the Amazon delivery truck. Something like, I mean, I don't know if these numbers are realistic, but something like given 200 addresses, how do we visit each one in the fastest route? That's the idea here. And that's why this is called the traveling salesman problem. People first started talking about this, 100 years ago, back in the day, of the traveling salesman, like a guy who would go around to people's houses and try to sell them stuff. And it's the same situation that guy has. He has a list of addresses that he wants to go to, and he wants to do it in such a way that he takes sort of the fastest route to reach each address once. All right? This is what the Amazon truck has to do. And they have to do this basically every day, right? Every time you load up the truck, you get a list of addresses, and somebody's got to figure out what route the driver should go. And I've never interviewed an Amazon delivery driver, but I've heard that they don't make many decisions on their own at all. Like, they are told exactly, first you go here, then you go here. So the guy in the truck is not having to figure out what the best route is. That is determined by some massive computer somewhere else. Because actually this is a hard kind of problem to solve. Anyway, this is what the traveling salesman problem is. Just one other application. So this is super important to people like Amazon, or it's not just Amazon. Anybody who does similar kinds of things, they need to be able to plan out these routes. Also, I'll just say this also comes up in efficient computer network routing. Right? This is a bit more abstract, but it's still, you get similar kinds of situations just in terms of like making the internet work. There are many kinds of situations when you are sending information from one location to another in the internet, and to find the best route from here to here or whatever, it often involves the same type of stuff. So this is not just about people driving around in trucks. This is also, it comes up in all kinds of other sorts of abstract situations. All right. I decided to, this morning, I asked ChatGPT to give me a joke about the traveling salesman problem. You ready for this? Some hilarity? I hope you all understand what the traveling salesman problem is by now. It says, why did the traveling salesman break up with his GPS? It's always about breakups. I asked another one, and it was about... All right, the answer is, because it kept saying, recalculating, shortest route not found. Eh? All right. This is actually, this is what a GPS has to do also, just to find the shortest route between one location and another. Now, that's not exactly the same as the traveling salesman. Just going from one place to another is a much simpler problem than saying, I have 50 places that I have to go to. I want you to tell me the best route to get to all 50. That's the traveling salesman problem. I appreciate that the ChatGPT kind of knows something about that, but yeah, not a great joke in my opinion. Okay, let's try some real kind of down-to-earth examples. I got one to try, and then I got one for you all to try. Let's try actually just this specific one about me and Megan and Gigi and Pops. I decided to look up these numbers as far as what the driving distances is. So this is my holiday travel graph. Now, it had 4 vertices, right? And they are, of course, in real life, those vertices are arranged on the, across the roads of our great land. But I might as well just draw them like this, right? There's 4 locations. We don't really need to arrange them according to the real geography here. And of course, there are these sort of diagonal edges, which represent going from one place to another. And I'm going to order them. I'm just going to label them by the states. So there's Massachusetts, there's Connecticut, and this is sort of my home. So we want our circuit to start and ending at the Connecticut location. I'll put the Pennsylvania and the New Jersey. All right. So this is, there's no reason to try and draw it in realistic geography. You might as well just look at it as a graph like this. And I looked up the distances in miles. These are the real distances from our houses to one another. And I'm just going to put them on the graph like this. So I'm going to put over here the distance to get from my house to my parents' house, which is 156 miles. The distance across the bottom is 152. All right? Almost exactly the same distance to my my wife's parents' house. Up the left side is 114. Across the top, this is from Massachusetts, Pennsylvania, is 355. And the two diagonals, so they kind of upwards diagonal, is 315, and the other one is 194. All right, so those are the various distances from one place to another in this graph. And remember, there is no vertex in the middle. So when I put this 315, that refers to this entire edge going across the diagonal, not like just to the middle. All right, great. Once you have this graph with the numbers on it, this is called a weighted graph. And those numbers on the graph are called the weights. The numbers are the weights. And in this problem, the weights represent distances, like real life distances. Although you can imagine variations of this problem. If instead of making the shortest possible distance, I said I want to make the shortest possible time, in this case they would be related to one another. But the weights could represent the times, or they could represent the cost of making these drives. If you had other costs associated, if there were tolls or something, you could try to minimize the cost, whatever. Anyway, those numbers are called the weights. And the traveling salesman problem, just to say it very clearly, the traveling salesman problem is given a weighted graph find the Hamilton circuit with the least possible total weight. All right, this is the technical way of describing exactly what the traveling salesman problem is. The problem is, if I show you a weighted graph, can you find me the Hamilton circuit with the least possible total weight? That is, you add up all the weights along the circuit and you want the smallest answer possible. All right? So, how do we answer this question? There are actually 3 different ways that we are going to talk about to answer the question, and they are the the last 3 things on our big checklist. There are other ways, because it's such an important problem in the real world. A lot of people have spent a lot of time working on solving the traveling salesman problem in various different ways. We're going to talk about 3 ways. So today, this is, I would say, in a certain sense, the easiest way to do this is what we call the brute force method. I put easiest in quotes because actually it kind of takes a long time to do this, but it's easy in the sense that there's nothing hard about it. It just will take you a while to add up the numbers and all of that. But there's no big hard ideas behind it. It's just, that's why it's called the brute force method. It kind of takes you a while to do it, but there's nothing hard sort of intellectually about it. Anyway, the brute force method involves you just list out all possible Hamilton circuits and then find the weights for each. And you choose the best one. That's all you got to do. You just list out all the possible Hamilton circuits, and then you figure out what the total weight is for each one, and you pick out, the best one. Right? So let's try that on my example here. Maybe I'll copy my picture down just so we can still see it. Here's my picture. So what we have to do is list out all the possible Hamilton circuits. Now, it's a bit of a pain the way that they're labeled here, the vertices. I'm just going to write C, M, P, and N, just so that I I'm going to be writing various ways that you could go from one to the other, and it's a pain to do it if they all have 2 letters. So what I'm going to do is list all hams. And like I said before, this is the same as just listing all possible reorderings. So they all look like C something 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 C, right? Because we want to start and end in at my house in Connecticut. And then the other 3 just going to go in there in some ordering, and they can be any possible ordering. For 3 things, there are 6 different ways that we could order them. So this is not so bad to actually list them all out. So my hams are C. Maybe I will just do the others starting, it can be any order you like. C, M, N, P, C. I put them in alphabetical order. The ones in the middle at least. All right, so that's my first one. That starts with M. There's one other way to start with M, like that, right? Those are the 2, start in the second position. I'm always going to have C at the beginning, but there are 2 that have M next. There are 2 that have N next, so that could be CN, MPC, or CN, PMC. And then there are 2 which have P in the second position. CPMN or CPNM, like that. There are 6 of them. If you have 3 different things to rearrange, there will always be 6 possibilities. All right? And now we have to find the weights. I want the total weight for each of these 6 different routes, and then we'll be able to see which one is the best. All right, so the numbers here are a little bit taxing, but I think we can handle it. So what we're doing for the first one, it says C to M. That has a weight, looking on the graph, C to M is 156. So this is 156 plus, I'm trying to add up the total weight. Next I have M to N, that's this diagonal, 315. Plus, next I have N to P. I hope everybody can see what I'm doing here. I'm looking edge by edge here and adding up the weights. So I did C to M is 156. M to N is 315. N to P is this one, 114. And then P to C is the other diagonal, 194. And this I added up. You can use a calculator for this kinds of numbers if you like. I got 779 as the total. That's the total distance of that route. All right? We got to do this for all of the other ones. This is a bit of a pain in this example because of the numbers. So the next one, again, says C to M, which starts with 156. Then we got M to P. This is different from before. So M to P is 355. Then we got P to N, that's down the left side, 114. Then we got N to C, which is 152. And this, when I did this, I added up to 777. All right, so that route is slightly better than the first one. What about the next one? So C to N first. That we begin with this one, which is a 152. Plus N to M is the big diagonal, 315. M to P is the one on top, 355. And then P to C is the other diagonal, 194. And this one I added up was 1016. That's the worst one so far. So we probably should not drive in that way. And so on. Would you mind if I just write out the other ones? I don't know if you need to copy these down, but for the next one, I got 152 plus 114 plus 355 plus 156, which adds up to 777. For the next one, I got 194 plus 355 plus 315 plus 152. This adds to 1016. And the last one, 194 plus 114 plus 315 plus 156. And here I got 779. All right. Here ends the adding the numbers nonsense. All right. This is kind of a pain to do, but there's nothing really hard about it. You just got to do it. All right. Anyway, now the whole point of this was you write down all the Hamilton circuits, which I did. You find all of their weights, and then you just choose the one which is the least. And actually, there's a tie. It's here and also here. So the best, in this example, there was a tie. The best route is CMPNC or CNPMC, right? Those are the two ones for 777 being the best possible total distance. All right? Only slightly different from the 779, but quite different, quite a lot better than the other one, 1016. All right. Excellent. This is what we call the brute force algorithm. That's because it'll take you kind of a little while, and you're just like adding a bunch of numbers together. But there's nothing, no big ideas really, nothing sophisticated going on. You're just grinding it out. All right. Did anybody notice these answers that I got? There are 6 of them here, but the answers that I got, like there's 2 777s, there's 2 779s, and 2 1016. Can anybody explain this? Is this a coincidence in this example? It's actually not. Anybody see why there's actually all of these answers? They come sort of 2 at a time. Yeah.
I mean, you're kind of going the same route, but like switching just one. Like,
Switching just
like
one.
for like the 2 777.
Yeah.
You're just switching the M and the N, so it's going to be the same number.
Right. Is that true? The other ones, like this, for instance, the one. If you look at the 2 1016s, these two, I think that.
You switch the P and the
I
N.
suppose the P and the N. Yeah. This is a good observation, and this is maybe the same as what I was going to say, but not quite. They don't have a maybe different way of explaining this. There's some relationship between these two. It is true that this involves just swapping those two guys. If you think about the routes that these look like on the map, CNMPC looks like that's this, right? Going around the outside this way. The other one, CPMNC, sorry, that's not this. CNM, it's this X, right? And the other one goes CPMNC. It's actually the same route. It's this X again, but going backwards. It's just doing the same route the other way around. So it is a fact, actually. In these lists, when you make a list like that, they kind of go together in terms of the answers. These are all reverses of one another. There will be 6 of them, but it's a guarantee that 3 of them will just be the reverses of the other 3. So if you're doing this on the homework or whatever, and you are annoyed with having to add all the numbers together, which you ought to be, you actually don't have to do all 6 of them. You only really have to do half of them, because the other half will just be reverses of the ones you did before. So I will say here, there's 6 possible routes, but really we only need to calculate 3 of them. Although it can be a little difficult to decide which 3 you have to do, but you can tell by looking at the letters. We only need to calculate 3 of them. The other 3 are reverses. And you can look sort of ahead of time at your big list. I mean, you can just look at these and tell which ones are reverses of the others. And so you can decide, you can save yourself some work in that case by just don't actually add them all up for all 6 of them. You only have to do 3 of them. All right. We got 10 minutes here. I got one for you all to try. I made the numbers quite a bit easier. I mean, these ones, there's no reason to do sort of big 3-digit numbers like that. So let's try find the minimal weight Hamilton circuit. I didn't invent a little real life scenario here. I'm just going to give you a graph with numbers on it. I'll call them A, B, C, D like this, and the numbers shall be like so. All right. Your job is, if I was writing this on the homework problem, I would just say something like solve the traveling salesman problem using the brute force method. All right? See if you can do it. It's just like the one we just did, only the numbers, these numbers you should be able to just do in your head. If I do give you one with weird numbers, you should use a calculator. But not on the test. I'll give you, the ones on the test will be more like this. As I'm walking around, I realized I didn't tell you where to start and finish. You can start and finish at any vertex. I saw most people are starting at A, which is fine. You can pick any starting point or any point. Sometimes I might say start and finish at a specific point. It doesn't matter. You should get 6 total different Hamilton circuits. There will always be 6. So if there are 4 verses, there will always be 6. So once you decide the first and last one,
Yeah.
you have 3 here, and just all different ways of doing things.
Okay.
But there's 2.
Okay.
But there's 2 of these verses.
Yeah. Okay.
Okay? Yeah. All right. Great. All right. Figure out what's going on.
Sorry, I just did it.
Just right when I was looking. You good here? You should be starting and ending with the same. And just like use A every time. Yeah. Yeah, they should all start and end at the same time. You good here? Yeah. Getting there. Alright. Yeah, if you want to be cute about it, you only have to add up 3 of them. Alright. Drawing some lines. You should make a big list of all the possible Hamilton circuits. You good here? started at A, so your numbers would be a little different, and the totals would be the same. All right, we're gonna go in a moment, so I'm gonna try and do mine here. Here's my six Hamilton circuits. I decided to start and end at A. If you started and ended at a different one, then you will, well, your totals will be the same, although the individual numbers will all be in different orders. So this one, the weights goes, A to B is 3, B to C is 2, C to D is 2, D to A is 1. So this is 3 plus 2 plus 2 plus 1 is 8. All right? I hope that you all got something like that. And maybe I'll just, as I'm doing them, I'll sort of indicate where's the other 8. There's always, these numbers always come in pairs 1 and it's reverse. So this was A, B, C, D, A. If I read this backwards, A, D, C, B, A, that's exactly the same edges, just in the other order. That's the last one. So this one also is 8. All right, and it's because these are the same path. And if you want to, do this on the homework or on the test or something, that's totally fine. You don't actually have to add up all 6 of them. You really only have to do 3 of them, and then the other 3 are reverses. Okay, the next one, A, B, D, C, A. That is A to B is 3, B to D is 4, D to C is 2, and C to A is 5. This, when I add up, I get 14. And the reverse of that, A, B, D, C, A, the reverse of that is A, C, B, D, A. That's this one, the very next one, right? So this one is also 14. Am I doing all right so far? I hope you get the same numbers. And then the next one, A, C, D, B, A. And these two next ones are also reverses of one another. A, C, D, B, A. So A to C is 5. C to D is 2, D to B is 4, B to A is 3. This adds up to 7. Did I write the wrong reversed? 8? Yeah, I did. Sorry, this is also 14, not the other one. I saw some people were giving me weird looks. It's because I chose the wrong one. Anyway, I still got 1 minute, right? A to C is 5. Sorry about that. C to B is 2. B to D is 4. D to A is 1. That makes 12. Am I right? And then that means this other one is 12 because those are reverses of one another and those. Anyway, the best route is A, B, C, D, A, or the reverse of that, which would be A, D, C, B, A for 8. All right? That's how we do it. See you all on Tuesday.